Alright guys, hello, and hope you guys are all surviving the apocalypse okay. Here we go, let's do some more chemical kinetics. Again, I just want to reiterate from the last video that if you guys ever have any questions about any part of this course moving forward, please make sure to email me or add me on Google and we can do a hangout chat. Okay, let's do a little bit of review because it's been quite a while since we have actually met in a class. So let's go back to basically what we're trying to do with chemical kinetics. So if we have some reaction, some generalized reaction, where we're reacting A to form some sort of product or multiple products, okay? We want to know how fast this reaction is going, okay? How quickly it's progressing. And the way that we determine to do that for a simple reaction like this is by using something called the rate laws. Okay? And the rate law is simply given by the rate of the reaction is equal to some constant K multiplied by the concentration of A raised to some factor N. Okay? Now remember, N is the order of the reaction, and K is a constant that we call the rate constant. And the rate constant and the order can only be determined by experiment. This can never be figured out just by simply looking at the problem itself. You have to do an experiment to figure out these quantities. Okay? These are empirical quantities. Okay? Now, for this value n here, you can have a couple of different common occurrences, or most common occurrences. So if you have an n equals 0, this is called a 0th order reaction. Okay, 0th order reaction. And the interesting thing about this reaction is that the rate is only dependent on, or actually, let's make it equal to. The rate is equal to the rate constant. Okay, so it is a constant rate. The rate of reaction is constant. It's not going to change over time. That's essentially what that means. And it's completely independent of the amount of A that's in the solution. The next common occurrence is n equal 1, and this is first order. This is a first order reaction. Okay, and when you look at this equation up here, what we have here when n is equal to 1 is we have the rate of the reaction is equal to K times the concentration of the reacting species raised to the 1th power. Okay? So now we have a rate that is dependent on the concentration of A, and it's dependent on the concentration of A raised to the 1st power. Okay? So this is called a first order equation. As A decreases, the rate also decreases, and it's a 1-to-1 decrease. Moving on to n equal 2. This is a second order reaction. Okay? And in this case, we have a rate that's equal to the rate constant times A raised to the 2nd power. Okay? And you start to see the pattern here. As you go higher and higher order, the rate is more and more dependent on the concentration of the species. Now, what we haven't discussed here yet, we went through and talked about how to actually figure out these values, the K and the order, or the K and the N, using this method of initial rates. Now remember, this is an experimental method, and we did that in class, and there's a few examples in the book. I'm not going to go back through that. I want to skip straight ahead to talk about the next step in these types of reactions, which has to do with multiple reactants. Okay, we haven't talked about this. We've only talked about the case where we have a single reactant reacting in the reaction. Say that 5 times fast. In this case, we want to look at something that's a little bit more complicated. So let's say A is reacting with B to form C and D. Oops. D. Okay. So this is our generalized multiple reactant species, multiple reactant reaction. And now we want to determine some sort of rate law that defines or define isn't the right word. Well, yeah, I guess it is the right word. Okay, it defines the rate that the reaction takes place. Okay, and it looks kind of complicated, but it actually turns out that it's very simple. We can write the rate law for this reaction by simply multiplying the rate constant for the reaction, multiplied by the concentration of A raised to the m power, and the concentration of B raised to the n power. Okay. M and n here are both orders of the reaction. Okay. M is the reaction order for B, or with respect to B, A, and N, in this case, is the reaction order with respect to B. Okay. However, the overall rate for this entire reaction, okay, so the total reaction, we want to know what the total rate is for this reaction. The overall rate is simply M plus N. Okay, so this gives you the total rate. But within the individual A and B, M is the reaction order for A in this case, and N is the reaction order for B. Okay, so they're separate. They're separate but similar, and you have to add them together to get the overall rate of the reaction. Okay, let's do an example here. Let's look at the reaction with, between hydrogen gas and iodine gas. Okay, what this forms is hydroiodic acid. Oops, I need my stoichiometric coefficient over there. Okay. This is the reaction we want to look at. We have two reactants here, hydrogen gas and iodine gas. We want to know what the rate actually is for this reaction. And after I do a bit of an experiment, I can find that the rate for this reaction is equal to K times H, or hydrogen raised to the 1th power, times iodine raised to the 1th power. Okay. So in this case, M is equal to 1, N is equal to 1. Both of these are first order with respect to their individual components. Okay? But actually, overall, the reaction is 1 plus 1 second order. Okay? So the total overall reaction is second order, even though each of the individual components are only first order. Okay, that's how it is. Okay, and again, the order and the rate constants are simply determined by experiment. There's no way that you can actually determine these by simply looking at the problem. Check my timer here. All right, we're good. Okay, let's do an example where we actually determine the rate constants, the rate constant and the order of the reaction. Okay. Let's look at the case where we have nitrogen dioxide gas reacting with carbon monoxide gas to form nitrogen monoxide and carbon dioxide gas. Okay, it's a nice little reaction. Let's do the method of initial rates and actually run some experiments and get some numbers out. Okay. So with this, we need some data to figure out the rate constants and the order. So pretend that I ran an experiment real quick. And by the way, I'm giving all of these concentrations in molarity. So I have the NO2 concentration and the carbon monoxide concentration in molarity, and I'm measuring an initial rate. And this initial rate, just like always, is in molarities per second. So I'm going to start out with concentrations of 0.10 moles per liter of nitrogen dioxide and 0.10 moles per liter of carbon dioxide, or monoxide. In the case of the first reaction, let's write a 1 over there, we have an initial rate of 0.0021. Next, I want to double the concentration of the NO2 and keep the concentration of the CO constant. Okay, so I'm only changing one variable, and we can see how the whole thing changes with a double in the nitrogen dioxide, and basically eliminating any changes from the carbon monoxide because it has the same concentration. And we see in this case that we have an increase in the rate from 0.0021 to 0.0082. Next, 3. In this case, we're going to leave the NO2 constant, and we're going to double the CO. So in this case, it's 0.020. Okay? And in this case, we have 0.0083. Okay? There wasn't much of a change there. And then finally, the last one we'll do, 4, is we will double NO2, and we will take 1/2 of CO, okay, and see what happens here. This gives us an initial rate of 0.033. Okay? So this is the data we would be given, or the data that we would measure to actually be able to determine the order and the rate constant. Okay, so in this first case, we have an NO2 increase by a factor of 2, so there's 2 times increase in NO2, and what happens over here is a 4 times increase in the rate. Okay. Next, we have an increase of 1 times in the NO2, so no change at all. And in the CO, we have an increase of 2x. And what happens over here is a change by a factor of 1. Okay, so there was no change with a change or with a double in the carbon monoxide concentration. That's an interesting hint. Okay, next we're going to again double the nitrogen dioxide concentration. And this time, instead of leaving this one constant, we're going to take this and multiply it by 1/2. See what happens. And we see that the rate between these two steps has again increased by 4x. Okay, so clearly something is happening here. And this behavior where we have the, let's do a little bit of different colors. How about red? Where we have the 4 times increase in the nitrogen monoxide with a 2 times, or in the rate with a 2 times increase in the nitrogen dioxide concentration, and again a 2 times increase and a 4 times increase in the rate. This suggests a second order reaction. So it's second order with NO2. Both of these suggest this. Okay. So that means that we have an order of 2 with respect to nitrogen dioxide. But what about carbon monoxide? So in this case, we're doubling it and we're halving it. And nothing else is happening to the initial rate. Okay. So these two experiments suggest that this reaction is has an order of 0 with respect to carbon monoxide concentration. Okay? So we have an N and we have an M. We can build the rate equation now. I'm going to switch back to black. So we have rate is equal to rate constant multiplied by NO2 raised to the 2 multiplied by carbon monoxide raised to the 0, which is simply just the rate constant multiplied by NO2 raised to the second power. Okay. Our overall reaction order is just the two orders added together, 2 plus 0. So that means that this is a second order reaction. And now all we have left to find is the rate constant. So remember, I can choose any of these above examples to actually measure or to calculate what the rate constant actually is. I'm just going to use one. Okay, so we have rate. I'm going to I'll just write it down here. Rate is equal to rate constant times NO2 raised to the second power. I'm going to rearrange this so that I have K all alone. K is equal to rate divided by NO2 squared. Okay. Now all I have to do is look at this first reaction here, look at my concentration for NO2, and look at my initial rate for this reaction. Plug those numbers in, and I should get, or I will get, my rate constant. So this would be, the rate for this one was 0.0021 molar per second, divided by the concentration for NO2, which I'm no longer going to put it in brackets, 0.10 molar squared. Okay. We have a cancellation of one of the moles, or one of the molar on the bottom and a molar on the top. And what we end up with when we actually compute this value is 0.21 per molar second. Okay, so this is the rate constant here. Now we can plug this back into the rate, and we can have our final complete rate equation. 0.01 per molar, that's a bad end, per molar second, multiplied by the NO2 concentration squared. Okay, this is our rate equation for this entire reaction. We can use this to determine the concentration at a specific time, or we can use it to determine basically how fast the reaction is going to take place, okay, at any point within the reaction. Okay, so this was a really obvious example, right? You increase it by 2, the rate went up by 4. You increase it by 2, the rate went up by 4. Actually, most of the time, it's not so obvious, okay? We don't get so lucky in life, right? Sometimes things are really obvious and really easy, but actually most of the time, they're not so obvious and easy at all, okay? So if it's not so easy, okay, so in this case, if not so obvious, how can we figure out the order and the rate constant for this reaction? We're going to use the same ratio method we used before for the single reactant species. Okay, so we have the ratio method here. Okay. And for this, you just take the ratios between two different rates, and from that you can you can always determine the reaction order. Okay, so even if it's super obvious, and you just want to make sure that what you're doing is correct, you can always use the ratio method, and I'll show you here. So we'll do it for this example. So let's find out the order for NO2 using the ratio method. So in this case, I'm just going to take the ratio of two different rates. I'll choose, it doesn't matter which one you choose. You can choose any. So I'll choose rate 2 over rate 1. And this is going to be K multiplied by NO2. And by the way, when you use the ratio method for a multi-component species, when you're only talking about one component, only use one component in the rate. Okay? So in this case, you have the rate constant multiplied by NO2 raised to some n value divided by the rate constant of NO2. Oh, this is for the second, this is for the first, raised to some value n. Okay, we can replace these with the numbers from above. Okay, so each of these we have numbers up here. We have numbers, and we're going to just plug those back in down here. So rate 2, the instantaneous rate, or the initial rate, was 0.00. Wait. Hold on, I'm confusing myself here. Surprise, surprise. Huh. Why is that like that? Oh, I see. I just have a mistake in my notes. My bad. Okay, so rate number 2 was 0.0082 divided by 0.0021. That's the first rate. Okay, and this is equal to the rate constant. Actually, the rate constants cancel, so I'm just going to ignore those here. Okay, these both cancel. I'm going to have my initial concentration for the second reaction, which is 0.20 raised to the factor of n, divided by the concentration for the first, 0.10 raised to the factor of n. Okay. So here I just compute these numbers down, and I get to 3.9 is equal to 2 raised to the n. Okay. I solve for n using the method of logs, so I take the logs of both sides, and when I do that, I can take this guy and bring it down front, right? You guys remember that? If you have log of x to the n, log of x to the n is equal to n times log of x. Okay. So I'm going to use that identity here, and I'm going to end up with n is equal to the log of 3.9 divided by the log of 2. Okay, and this, when you compute these numbers together, is 1.96. Okay, we have a significant figure here. So this is going to round up to 2.0, and we get an n equal to 2, which is exactly what we predicted without using the ratio method. Okay, let's do it quickly for carbon monoxide. Carbon monoxide will use rate 3 divided by rate 2. And again, you can use whatever rate you want. This will be the rate constant divided by CO to the n for the seconds. Again, rate constants cancel out, and we can just plug these numbers in. So I have 0.0083 divided by 0.0082, and this is equal to 0.20 raised to the n divided by 0.10 raised to the n. If I solve this out, I find that 1.01 is equal to 2 raised to the n. Okay, and what we get in the end is n is equal to 0.01, which rounding in this case would just be 0. Okay, so n is equal to 0 in this case, n is equal to 2 in this case, and then we can build our rate law just like we always do. Okay, here I'm going to pause, and I'm going to upload this video. Oh, there's my timer. Perfect timing. I'm going to pause this video and upload it so that each of the videos are going to be only about 25 minutes. Even though the whole period is about 55, in the end it'll kind of work out. I just wanted to break it up so it's not so crazy. Give you guys time to maybe stretch it out a little bit, maybe look through your book, go over your notes, do whatever. Okay, so we'll be back for part 2 in just a second. Okay, see you then.